Hi everyone, I'm Vinu from the University of Maryland. I'm here to present my work CUDA, Convolution-based Unlearnable Datasets, which is a joint work with Mahdi and Soheil. Here is a 1-minute pitch of my presentation. In the game of unlearnability, an attacker adds noise to training images. A defender trains a network F using these images. F achieves good accuracy on the unlearnable images, while it performs poorly on the clean images. Unlearnability could be used in privacy applications. For example, my advisor Soheil could upload his unlearnable profile pictures to social medias. An adversary F trained on these images will not detect Soheil in clean images or in real world. We introduce CUDA, which adds novel non-additive noises via convolutional blurring for unlearnability. CUDA is more robust and faster when compared to the previous methods. Previous methods require nested optimizations for creating unlearnable images. Error minimization by Huang et al. Proposed to use a min-min bilevel optimization for generating delta i's for each image xi that can be added in an imperceptible manner to generate unlearnable images. Fowl et al. Proposed targeted adversarial poisoning that uses a min-max optimization. However, both these methods are expensive and not robust to adversarial training. To make unlearnable images that are robust to adversarial training, Fu et al. Proposed robust error minimization, which uses a tri-level min-min-max optimization. However, this method is very expensive, time-consuming, and not transferable to DenseNet 121 architecture. We also show that it is very sensitive to the hyperparameters of adversarial training, and REM breaks with very simple augmentation such as grayscaling. CUDA R method is a very simple approach. It is model-free, and it does not require any training or optimization. So for a given clean image x, y, we generate a filter sy randomly for each class y. As shown in the figure in the right, sy is a matrix of size k cross k. So the center parameter of the filter sy is fixed to be 1, while the other parameters are uniformly sampled from a distribution between 0 and pb. Now, PB is the blur parameter, and PB and K together controls the amount of blurring that CUDA performs on the clean image X. So now X dash is created by convolving X and SY together. And the CUDA image is basically the rescaled version of X dash such that all the pixel values are between 0 and 1. CUDA encourages a network to learn the relation between SY and Y rather than the clean image X and Y. And hence, we could probably assume that the network might not be learning any useful information about the image for classification. CUDA is effective, and we show that our method is 20 to 100 times faster than the previous method since it's model-free. As shown in the table here, our method takes only order of seconds for creating unlearnable datasets, while the previous techniques takes order of hours for creating unlearnable datasets. We show experiments to demonstrate that our technique is robust to adversarial training, augmentations, and adaptive defenses. We also show that it's transferable to different networks and works with multiple datasets. We show theory for CUDA on a Gaussian mixture data. So our informal theorem states the following. Let D be a Gaussian mixture with two modes, and PD denote optimal Bayesian classifier trained on D. We show that for a clean dataset D, there exists a CUDA dataset D dash corresponding to D, such that a Bayesian classifier trained on D dash will have a poor generalization over the clean dataset D. In our experiments, we show that CUDA is very robust to adversarial training under different training settings. For example, in the table here, we use different hyperparameters and attack budget in adversarial training to show that CUDA is very effective with multiple datasets. The best accuracy which can be obtained on the CUDA dataset using adversarial training is much lower than the accuracy you can see or obtain using the clean dataset. We also show that CUDA is robust to different networks and datasets. For example, we show that our network is our technique is robust to ResNet 18, VGG, wide ResNet, DenseNet, MobileNet, EfficientNet, and Image Transformer. We also show its effectiveness on CIFAR 10, CIFAR 100, ImageNet, and Tiny ImageNet. So as shown in the table here, CUDA is the only technique that is consistently robust with different networks with adversarial training. CUDA is also robust to other defenses such as data augmentations and adaptive defenses. We show that CUDA does not break with mix-up, cut mix, grayscaling, or randomized smoothing. We also design an adaptive defense where we use, which we call as a deconvolution-based adversarial training. So here the defender uses the CUDA dataset to learn a deconvolution filter to reverse the effect of CUDA. However, as shown in the plot here, we see that for a smaller blur parameter PB, deconvolution-based adversarial training is successful. However, for a reasonably large blur parameter, we see that CUDA is still effective and provides good unlearnability effects. Hence, there's a trade-off between stealth and unlearnability with CUDA. We invite you to come to our poster presentation at CVPR for our work. That's all. Thank you.